This video, we're going to talk about the exercises from 2.2 and Apex Pre-Calculus, solving inequalities. Problem 1 asks us, in your own words, explain what is meant by a strict inequality. It's going to be a strictly less than or strictly greater than without the inclusion of the boundary points. It's not going to be less than or equal to with the line underneath. It's not going to be greater than or equal to with the line underneath. It's just going to be strictly less than, strictly greater than. It's not going to be less than or equal to or greater than or equal to. Okay. Your own words describe two ways we can have breakpoints. So we can have breakpoints from a polynomial being polynomial inequality is one of the ways that they showed. We can also have a rational inequality. When we have a rational inequality, we can have breakpoints from the numerator equaling 0 or from the denominator equaling 0. We also just have breakpoints in our domain whenever we're going to break any of the rules for domain that say no division by 0. So that's one of the things in a rational inequality that we have to watch out for, but we don't have to watch out for in polynomials. And then we also have to watch out for the discriminant of even indexed roots must be non-negative. Talk about that some more in a little bit. So if we have something inside of a square root sign, it can be equal to 0, it can be greater than 0, but it can't be less than 0 because we don't take square roots of negative numbers and get real answers. We talked about that with our section on factoring and solving. Does a statement always switch from true to false at the breakpoints? No, it does not, because it depends on the multiplicity of the root. If the multiplicity is even, it's going to not change sign, not change truth value when it crosses that 0. Only if it has an odd multiplicity will it cross. So let me give you an example. F of x is equal to x minus 1 squared times x plus 2 times x minus 3 to the third. And I want to find where f of x is above the x-axis, so greater than 0. So my zeros are going to be at 1, -2, and +3. I personally am going to start all the way to the right over here because I know when I have all positives that this is positive. When I cross 3, which is where this 0 is coming from, it's an odd multiplicity. It's going to change truth value from positive to negative here. It's going to change sign. When I cross the boundary of 1, though, it's an even multiplicity. It's not going to change the sign or the truth value. Then when I cross 2, it's an odd multiplicity, so it is going to cross. Go ahead and it is going to, I'm saying cross because it's going to cross the x-axis, but in this place where it's not changing sign, it's touching the x-axis. So we get an idea that we're starting off above the x-axis, then we go below and we cross here. And then we're going to touch here because we're going to stay below and then we're going to cross again. We're going to go above. So I can't tell you exactly what this graph looks like, but it's something like this. -2, +1, and 3 are my zeros. I'm above the x-axis over here. Then I'm below the x-axis. I'm going to come up and I'm going to touch. Let's see, this is going to be 1, 2 is 2, -27. I'm going to come down here. Then I'm going to come back up. I'm going to cross through. And so I cross, touch, cross, just like it shows my pattern here. I'm above, then I'm below, and I stayed below between -2 and 1. I've got my y-intercept kind of figured out here, that my y-intercept when x was 0 is going to be 1 times 2 times -27 is a -54. So I just guesstimated that down there. And then I'm coming back up. All right. That is an example, a counterexample of saying that it always changes truth value at a breakpoint. What methods can you use to find the breakpoints of a quadratic inequality? So I can use a number line like I just showed you with a sign chart. Use an actual number line. I can use a sign chart. And there's a more complicated table that I can use. It's not just the number line with the signs that I was using. I can use test points. All these things are covered in the text earlier. So, and your teacher in class should go over this with you and give you plenty of examples and show you how he or she wants you to solve them. We're typically going to use factoring to find the breakpoints. And if factoring doesn't work, we may need to use the quadratic formula to find some of them. Some of them just may not have zeros as some of the factors. So, all right, we're going to write number 5 in interval notation. This is very important that you learn interval notation. The left boundary point is included. The right boundary point is also included, so I use brackets to represent that. Number 6. I'm going to start off with a number line here that says x is greater than or equal to -5. And x is less than a +2. So less than, but not equal to. So that's going to give me an interval from -5 to 2, like that. Oh, I just did number 7 instead of number 6. So apologies. This is number 7 because it says x is less than 2, which is what I read, but that's not what it said. It said it's greater than or equal to -5 and greater than 2. So anything greater than 2 is going to be greater than -5, but not everything greater than -5 is going to be greater than 2. So I need to look at the intersection of greater than or equal to -5 and greater than 2. So the intersection between these two is this part, which is greater than 2. That's number 6. So everyone follow that. Watch your direction of your inequality signs here. Number 8 asks me x is less than or equal to -5 and x is greater than 2. So is there any place where I can be less than -5 and at the same time be greater than 2? There's no solution to this because there's no point of intersection. So it's the empty set is how we can express that. Or we can write an empty set like this, a null set. Number 9, x is greater than or equal to -5. Or x is greater than 2. Well, now I'm going to take the union of those two things with or, not the intersection. So when I combine them, that's the same thing as saying it's greater than -5 because both of them go off to infinity there. So it can be in either area, either part that's true will make it true. So I'm going to actually, let's take a second to talk about that because you may not know about ands and ors. So let's talk about I'm just going to write it out with words, not with symbols. So if I say or, then any part that's true is going to make it true. If I say and, then they both have to be true for it to be true. So this is what we call an intersection in Venn diagrams. I'll talk about that in a second. This is what we're going to call a union in Venn diagrams. So if I had A and I had B, A union B is the same thing as the or here is going to be everything that's in A and everything that's in B and everything that's in both of them. If I had a Venn diagram here and I had A intersect B, that's the same thing as the and. It's only what's in both of them. So the one that looks kind of like a letter A is going to be and. The one that looks like a U is going to give me a union. This is going to be an intersection. Okay. Where were we at? We were at number 10, I believe. So we've got 4 less than or equal to and greater than -6, like that. So we've got -6 to 4. 11 says greater than 4, less than 2, 4. Less than 2, less than -2, excuse me. -2, greater than 4. There we go. So we're going to have 2 open intervals from -infinity to -2, union 4 to infinity. Now we're going to write some statements using inequalities. So we're going to look at something that's already in interval notation. And we're going to say that, let's put it on the number line. 3 to 4. 3 is included. 4 is not included. And then we have 4 to infinity. So we have x is is between -3, 4, or x is greater than 4. That's one of the ways that I can express that. That's number 12. Number 13. I could have also said for this one, x is greater than or equal to 3, and x is not equal to 4. That's another type of inequality we haven't talked about, not equal to's, but I could have just removed that one point from this inequality here, and that would have been okay too. Both of those would have worked. X is going to be greater than or equal to -2, and it's going to be less than 4. Or I could write it this way. With a compound inequality like that. 14 is x is between 5 and 6, or x is between 7 included and 8 not included. That seems to be the best way to write it there. Now let's look at number 15. So we have the expression x minus 2 divided by x minus 4 needs to be less than or equal to 0. I'm just going to use a number line. I'm not going to use a graph here. I'm going to start off with my domain tells me that I can't be equal to 4 because I can't divide by 0. Then I'm going to look for the zeros of my numerator. They're going to be at 2. They're allowed to be included. I'm going to put a solid dot there. And then I'm going to look over here. It's going to be a positive divided by a positive. It's going to be positive. This is an odd multiplicity, so it's going to change sign when I cross that breakpoint. This is an odd multiplicity, so it's going to change sign when I cross that breakpoint. I'm looking for where it's less than or equal to, so I'm looking for where it's negative. So my answer should be 2 to 4. Number 16 says x squared minus 2x plus 8 less than or equal to 2x plus 5. I've always got to get a 0 on one side to make sure my x squared term is positive. So I'm going to subtract 2x from both sides. I'm going to subtract 5 from both sides. It's going to give me x squared minus 4x plus 3 is less than or equal to 0. Now I'm going to factor the side that's not 0. X and x, both signs are the same. They're both negative. I have 1 and 3. -1 and -3 add to give me -4. And I put them on my number line. There's 1 and there's 3. Both of them get included because 0 is included. I'm going to start on the right. It's going to give me positive, then negative, and positive because I have odd multiplicities on everything. Less than or equal to 0. So I'm in the negative portion from 1 to 3, both endpoints included. 17, x squared plus 2x is greater than 15. I'm going to subtract 15 from both sides. Then I'm going to factor plus 5 minus 3, multiply to give me 15, add to give me 2. Let's put those on my number line, -5 and +3. My factors are all with a exponent of 1, so I'm going to change sign every time. I want greater than 0 now, so my endpoints are not included. I'm going to have -infinity to -5 union 3 to infinity. 18. -x squared plus 7x plus 10 is greater than or equal to 0. I don't want a -x squared, so I'm going to divide by a -1 for everything. When I divide or multiply by a negative, it's going to change the direction of the inequality sign. So that's going to change from greater than or equal to less than or equal to. I alternatively could have just factored a -1 out, but that's harder to keep track of. So factors of 10 have a difference of 7. Not happening, right? So let's go ahead and solve this with the quadratic formula. So x is going to be equal to -b plus or minus the square root of b squared minus 4ac all over 2a. It's going to be equal to 7 plus or minus root 89 over 2. This is bigger than 9, smaller than 10, right? So let's pull out our calculator here just to get an estimate for what this is. 7 plus the square root of 89 divided by 2. So on this end is going to be 8.217 roughly. This is actually equal to 7 plus root 89 over 2 is exactly what's there, but I need to know about what it is here so I can test a number bigger or smaller than it. On the left-hand side, I'm going to have minus. This is going to be -1.217 approximately, which is 7 minus root 89 over 2. And we said that the endpoints are going to be included. And we want something that is going to give us less than 0. So over here, this is going to be positive. This is going to be a odd. This is only going to be a factor one time, so it's going to change sign when I cross, and then it's going to change sign again when I cross over here. And so I want something that is less than 0 in here. So my answer in interval notation is everything between 7 minus root 89 over 2 and 7 plus root 89 over 2. That's my exact answer. x plus 3 over x minus 2 with a minus 2 outside of it, less than or equal to 0. So I'm going to make a common denominator of x minus 2. That's going to be x plus 3 minus 2x plus 4 over x minus 2 is less than or equal to 0. This doesn't change the domain at all. It just writes everything as a simplified fraction. That's a negative x plus 7 over x minus 2 is less than or equal to 0. So I'm going to pull out that negative sign like that. And I want to get rid of that negative sign if I can by changing the direction of the inequality sign. So now we've got 2 and 7, but 2 can't be included because it'll make division by 0. 7 is going to be included because the 0 of the top is going to make it equal to 0, and that's included. This is going to be positive, negative, positive for my signs because these are all odd multiplicities. So now we're going to look for where it's greater than or equal to 0. That's here, and that's here. So my answer in interval notation is going to be negative infinity to 2, not included, union 7 to infinity. That was 19. On to number 20. 20 says 2x squared minus 4x minus 45 is less than or equal to negative 4x plus 5. So when we add 4x to both sides, that goes away. We subtract 5. We get 2x squared minus 50 is less than or equal to 0. X squared minus 25, x plus 5, x minus 5. That 2 isn't going to hurt anything. Negative 5 and 5. And we want positive, negative, positive for our signs. We don't want less than or equal to 0. So we are in between the breakpoints, negative 5 to 5. 21 is a lot like 19, but they haven't brought the 2 over. 3x plus 1 over x minus 2 is less than or equal to 2. So I'm going to have to subtract 2, get 0 on this side, and then I'm going to have to make my common denominator by multiplying by x minus 2 over x minus 2. 3x plus 1 minus 2x plus 4 over x minus 2 less than or equal to 0. It's going to give me x plus 5 in the top, x minus 2 in the bottom. 2 is going to be, so you have a negative 5 here. It's included, and I have a 2 there that's not included because of the domain. And we said less than or equal to. This is going to be positive on this side, then negative, then positive. Less than or equal to is going to be in here from negative 5 to 2. (22) is going to be 1 plus x less than 7x plus 5. Let's just show you something. If I get 0 on this side, that's going to be 6x plus 4. Now we can switch the direction of the inequality like so to keep it true. 6x greater than -4, x greater than -2/3. We go -2/3 to infinity. I don't need a number line for that because it's a strict inequality. But if you want it, here's -2/3, not included, and I need to be greater than. (23) says theta squared minus 5 theta is less than or equal to -6. Theta squared minus 5 theta plus 6 is less than or equal to 0. Theta plus minus, minus, both are the same, both negative, 2 and 3. So this is going to be plus, minus, plus. I said or equal to, so those can be included. And we want less than or equal to, so we are there from 2 to 3. You're allowed to put theta as an element of if you would like to, or x as an element of, like they had done up here. That's what that little e means, is an element of. (24) y to the third plus 3y squared is greater than 4y. Y to the third plus 3y squared minus 4y is greater than 0. Strictly greater than this time. I'm going to factor y out as a greatest common factor. Then we have y plus 4 and y minus 1. So factors. We're going to have open circles everywhere that we have a 0 because the zeros are not included. -4, 0, and 1 are all breakpoints. Over here to the right, when everything is positive, this is positive. Everything's an odd multiplicity, so I'm going to change signs every time that I cross. They've not given me one yet with a repeated root. Now I want only the things that are greater than 0, so the positive areas are greater than 0. That's going to be -4 to 0, union 1 to infinity. 25, x cubed minus x squared is going to be less than or equal to 0. So x squared, x minus 1, less than or equal to 0. I was just talking about we haven't had a repeated root yet, and here it is. That we have a repeated root at 0. So we have 0 and 1. Start out over here that this is going to be positive. I'm going to include the breakpoints because it says or equal to. There's an odd exponent on x minus 1, so we're going to change sign. There's an even exponent on the x minus 0 part, the x, so we're not going to change sign. So we want less than or equal to. It's there. It's also there. And since I include this point 2, it's everything from -infinity to 1. I don't have to stop at 0 and start again because it was included. So all that was shaded from -infinity all the way over to 1. 26, x squared plus 3x plus 2 over x squared minus 16 greater than or equal to 0. So we're going to factor the numerator, x plus 1, x plus 2. The denominator, we're going to have x plus 4, x minus 4. It's going to be greater than or equal to 0. So on my number line, I'm going to have -4. It's going to be open. +4 is going to be open because I can't divide by 0. -2 is going to have a included boundary point because this says they're equal to. And -1 is also going to have an included boundary point because this is or equal to. All of them are odd multiplicities. So I'm going to start over here to the right as positive, then negative, then positive, then negative, then positive. I want greater than or equal to, so I'm going to shade my positive areas. We've got 3 parts to this answer, -infinity to -4, union, this is included, -2 to -1, union, 4 to infinity, it's not included. I believe that's everything for this one. That's it. So next time we're going to come back, we're going to talk about domain a little bit more. I mentioned it this time, but we're going to mention it more specifically and how these inequalities play a part in it, because we're going to say we're not allowed to divide by 0, which we just did with rational inequalities. We're also not allowed to take the square root or any other even root of a negative number. So we're going to get one of these inequalities with a greater than or equal to 0 in it when we do that. So that's why we were setting this up that way. We'll also have the domain of any log functions have to be strictly greater than 0, the inputs. We'll talk about that next time.